Hello everyone, my name is Anirudh. I'm going to present developing sim to real multitask recommendations via open-ended learning. This is a joint work with my colleagues Masahiro Esuda and Shusaku Yosa at Zozo Japan. Recommendation systems seek to solve information overload by searching through large collection of dynamically generated information in order to provide users with personalized content and services. For example, Netflix delivers personalized material like movies and TV shows through recommendation systems, and Pinterest provides billions of pin recommendations to millions of users in order to engage users and drive business through revenue. Collaborative and content based recommendation systems are two of the most popular types of recommendation. Collaborative filtering based methods try to recognize commonalities between users on the basis of their ratings and generate new recommendations based on inter-user comparisons, whereas a content-based recommender learns a profile of new users' interest based on the features present uh, in the objects the user has rated. Recently, collaborative interactive recommenders, especially those based on reinforcement learning techniques, have gained attention due to their ability to model long term sequential user interactions and also overall improve overall satisfaction. For example, YouTube studied the impact of belief state approximation in slowly evolving, highly noisy latent state reinforcement learning problems such as recommendation, and demonstrated that long-term value estimation using slate queue method can improve user engagement significantly. Similarly, Spotify showed that a diverse consumption of music is strongly associated with important long-term engagement metrics such as user conversion and retention, and used RL sequencer to improve the overall satisfaction of the users. Previous research on RL-based methods for recommendation systems have focused only on maximizing single type of user responses like impressions, click, and buy. But real-world recommender systems have many challenges. They have to deal with multiple recommendation tasks and maximize many types of user responses simultaneously. In order to simultaneously maximize many types of user responses, large amounts of interaction data and computation is required, which is expensive. Recommendation system operates in a latent state Markov decision process. Hence, it must capture various aspects of user state, for example, uh, interests, preferences, satisfaction, activity, mood, that generally emit uh, noisy signals via the user's observed behavior. Moreover, exogenous, unobservable events further complicate the interpretation of users' behavior. Hence, recommender systems must learn to act in environments that have severe partial observability and stochasticity. In this work, we seek answers to the following intriguing questions. Can we generate complex training environments that cover unknown real-world challenges without having to program them ourselves? Can we develop a framework that captures multi-signal to infer true user utility while maintaining training and training serving efficiency? Self-play has been behind many of the prominent successes in AI, largely due to its ability to generate a natural curriculum of increasing complexity. Open-endedness is a type of self-play. It can continue to generate new tasks in a radiating tree of challenges indefinitely, along with agents that can solve these expanding set of increasingly diverse and complex challenges. Unfortunately, the zero-shot generalization and transfer capability is limited narrowly to symmetric zero-sum games and simulators. We want to extend this success far beyond these limited domains. We hypothesize that with enough diversity in the simulator, the real world may appear to the model as just another variation. To this end, we cast this recommendation problem as open-ended learning problem, where an agent endlessly generates increasingly complex challenges and simultaneously solves them in an autonomous fashion. We formulate the recommendation problem as a Markov decision process. We denote set of recommendation tasks such as ranking to maximize click response, buy response, and impression response as T. These tasks differ in their reward functions and their transition functions. Then, for each task, we aim to jointly maximize the discounted return. We adapt the algorithm discussed in the paper POET to a recommendation setting. The three important features of the algorithm that makes it suitable for recommendation setting are novelty search, where the offsprings are chosen based on their behavioral divergence from archive of individuals from previous generations, allowing algorithm uh, to discover novel complex challenges. Quality diversity that ensures that the algorithm not only discovers increasingly difficult challenges, but also learns to solve them. Goal switching encourages knowledge sharing by periodically testing the performance of the offspring agent on one environment in another environment. For multitask learning, we adopt a shared bottom architecture as illustrated in the slide. The input to the policy network is a state S, and the output has NT task-specific branches. Each branch has NI task-specific layers and captures the distinct part of the policy. All the branches share the first NS layers at the bottom to facilitate knowledge sharing among different recommendation tasks. The output of the ith branch is action AIT, where actions are determined by a stochastic policy function. We conduct large-scale experiments on real-world e-commerce platform. We apply open-ended learning to recommend or rank modules on ZozoTown homepage. Here, a module represents a group of similar items. Our aim is to recommend the right set of modules to the users to drive user engagement, satisfaction, and revenue. We build a collaborative interactive recommendation simulator using Rexim framework. We model the reinforcement learning recommendation environment as discussed in the paper Advantage Amplification and Slowly Evolving Latent State Environments. Overall, the document sampler samples modules from prior distribution of module features. The user sampler samples users from prior distribution of user features. To simulate user response on ZozoTown, we developed a multinomial choice model based on a simple cat boost model that uses user state and module features and predicts the probability of the user's action for each task. The agent then receives these inputs as state and uses policy network to predict the coefficients of a ranking formula as actions. Weighted multiplication-based ranking module combines these predicted actions to a final score through a combination function and then recommends the top modules. The transition functions are then used to update the document and user states, and the rewards from the reward functions are used to update the policy network. Please refer to the paper for more details. To monitor the progress of open-ended learning, we maintain a counter as proposed in Enhanced POET and track the accumulated number of novel environments created and solved over the course of run of an open-ended system. The increasing ANEX score versus time graph in the slide indicates that the algorithm is constantly creating meaningful, novel environments. While we train the supervised methods and multitask learning methods on an in-house real-world dataset with millions of interactions, our method uses inexpensive simulator-based learning. We then evaluate all the methods on a held-out test dataset. The current slide shows the dataset statistics for a training and offline evaluation dataset. Normalized discounted cumulative gain (NDCG) and mean average precision (MAP) are widely used ranking metrics in information retrieval systems. Hence, we use NDCG and MAP as recommendation evaluation metrics. We first compare the results of our method against supervised approaches like logistic regression, factorization machines, Bayesian personalized ranking based loss factorization machines, and neural collaborative filtering. As shown in the slide, our method uh, performs superior against uh, supervised methods. Supervised learning methods cannot plan the recommendations in a way that considers long-term reward. They also follow a single task learning framework and thus fail to take advantage of the knowledge from other tasks to improve their performance on each task. On contrary, open-ended learning agent makes recommendations by maximizing the rewards in the longer horizon and encourages knowledge sharing through jointly learning multiple recommendation tasks. We also compare results of our method with other reinforcement learning based techniques. Evolutionary strategies (ES) method is based on single task deep reinforcement learning. The open-ended learning agent shows better performance in all recommendation tasks. This may be due to the fact that the stepping stones that lead to solutions to very challenging environments are more likely to be found through a divergent open-ended process rather than through a direct attempt to optimize in the challenging environment. Finally, we compare our method with other multitask learning based methods. Although both sets of methods follow multitask learning framework, our method aims to maximize long-term rewards in making recommendations and takes into account the impacts of current recommendation to future rewards. Hence, our method achieves superior results over other uh, multitask learning methods. In this work, we introduced a few real-world challenges in designing and developing industrial recommendation systems, especially ranking systems. We showed that open-ended learning can improve transfer and generalizations in such recommendation systems. Multitask learning architecture can also improve the overall performance of the model through knowledge sharing and also reduce the computational costs. Thank you.